So far what we've been doing is looking at variance and mean having to do with single values, but never probabilities. Well, when we looked at our game yesterday, Chuck-a-Luck, the expected value is when you took the number, remember that game we played yesterday? Okay, that game, if you took the value of the money you won times the probability and added those up, remember we had $1 for, I think it was 1 out of something. Let's say it's 1 out of 10. And then you lost $1, so you go minus 1 times whatever that probability, 1 out of 20, and so on. You added those up, you get the expected value. So the expected value is the number times the probability added all those up. We're going to just call that mu. For a probability distribution, we're going to call that mu. If you go to a holiday store and go to the back of the store, you'll find they, by law, have to give you each game and what the probabilities of each game is and the expected value. And each one is about minus 30 cents per the dollar. So you give them $1. Every time you play, expect to lose 30 cents. Is that a good idea? No, and nobody should do it. But whatever you want to do with your money is up to you. I have never spent $1 on a lottery ticket, and I never will. Never put money down on a gambling game because the games are all set for you to lose. If you look at expected values of two functions added together, you can add the expected values. That's boring. But when you put these together, what happens is that if you are looking at an expected value of like a linear function, what you can do is pull the a out in front, a e of x, and this constant doesn't do anything to the expected value. It's still, the distribution is the same, and so they just add the b. This is kind of huge. Would you put a star next to this? IB runs, sometimes we run into this one and this one down here. The variance is e of x squared minus e of x quantity squared. We've kind of seen that a few times. But if you see a linear distribution in that variance, the variance doesn't matter if it's moved up at all. That won't have any bearing, but the a will have a squared effect to it. And I'm not going to prove that, but these two, would you have little stars next to that? We'll be using that in the future. Might be. I don't ever believe it's going to be there. For binomial distributions, this is the cool one with the flipping a coin. If I flip a coin once, what's the chances of getting heads? 50-50. If I flip it twice, what's the chances of getting one head? Right, exactly. So let's look at it. You could have heads, 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 tails, tail, head, and tail, tail. So what's the chances of getting one head? 1/2. There's 2 out of 4. The first one could be a head or the second one could be a head. You good with that? Okay. And of course, the chances of getting 2 heads is 1 out of 4. Now let's say we flipped it 3 times. What are the chances of getting 1 head this time? Yeah, it's head, head, heads, 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 tails, heads, tail, heads. Oh, this should be head. So then you can put, you got head, 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 tail, head, and then you can go head, tail, tail, right? And then you can go tail, 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 head, tail, heads, tails, and tail, head, head, and any other ones? Eight, yeah, okay. So what are the chances of getting one of those as a head? There's this one, and this one. Yep, 3 out of 8. Okay, how about 2 heads? 3 out of 8. How about 3 heads? 1 out of 8. So interesting, for the number of heads, 0, 1, and 2, here's what the probability distribution looks like. It was 1 out of 4, 2 out of 4, 1 out of 4. Now for the next one, if you had 3 coins, 0, 1, 2, and 3, that probability distribution is going to look like this. It's going to be 1 out of 8, and then this you said was 3 out of 8, 3 out of 8, and 1 out of 8. What do you notice all these add up to? 1. What do these all add up to? And Will notices something else. This 1, 3, 3, 1 looks familiar to me. This 1, 2, 1 looks familiar to me. Pascal's triangle, 1, 1, 1, 1, 2, 1, 3, 3, 1. What if we had 4 coins? Let's not do the probabilities. What's it going to be? 1, 4, 6, 4, 1 over what will all of these be? 16, right? 2 to the 4th. Okay. Could you do 5 coins? 6 coins? All of those, yeah. And so what happens is that we see that this binomial distribution, that means a couple things. Would you write a little note here? Note. Must be yes or no. I don't want to say pass or fail. It sounds so negative. Must be yes or no. Either a head or it's not a head. It's a tail or it's not a tail. The other thing is there's specific number of trials. So it isn't an indefinite number of trials. So this is number 1, this is number 2. And I think that's good. That's good enough. So then for success, you have P. Failure will have to be 1 minus P. That's the failure. Okay? So as you saw before, for if you had the heads and tails thing, the probability of getting a head is 1/2. What's the probability of getting a tail? 1/2. So you go 1/2, 1/2. If this were 1/3, this would be, Q would be 2/3. And so what you're going to do is this n choose x has to do with the number of ways that it could come up. And I like the flipping a coin 10 times. How many ways could one head turn up? 10 times. If you flipped a coin 9 times, one coin comes up 9 different ways, just like your Pascal's triangle. Okay, so in your calculator, there's actually a binomial distribution, and you put the trials first. You put the probability of success next, and then how many you want, like 2 coins, 2 heads or 3 heads next. And you can actually calculate all these. The formula is n choose how many you want, probability to how many you want, fail to n minus how many you want. So let's just do a couple of here. A manufacturer finds that 30% of the items produced from an assembly line are defective. So the probability of something being defective is 0.3. What's the probability that it's not defective? 0.7. 1 minus 0.3. During a floor inspection, the manufacturer selects 6 of these items. Find the probability that the manufacturer finds 2 defectives. So the probability is 0.3. The fail is 0.7. The number we're looking at is 2. And we're selecting a total of how many? 6. Yeah. Oh, this is awesome. We can do this. We can do this. N choose x, t to the x, q to the n minus x. So here goes. We're going to take, of the 6, I want to see 2 defectives. Probability they're defective is 0.3 to the 2, because there's 2 of them. But there'll also be how many not defectives? 4. Yep. So you're going to need to use your calculator to help out with this one. This is 6 choose 2, which I can do in my head. Can you do that in your head? 6 factorial. 6 times 5 times 4, 3, 2, 1 over 2 times 1 times 4, 3, 2, 1. This will just be 15, won't it? Right? That's okay. All right, so it's 15 times, what does this whole thing turn out to be? Oh, did you get it? Point what? 324. Anybody second that? 3 decimals is great. Love it. So there's your, about a 32% chance. Now, I'm going to teach you something that's going to save your probabilistic life. You are going to always do well on these problems forever because you're going to use my technique. If you looked at all of the possibilities that could be, you have 6 objects, you could look at the probability of selecting how many defectives? 1, yep, I like it. What else could you get for defectives? 0, and you could get 2, right? So these are all of the possibilities which should add up to 1. Do you agree? So write that down. I could get 0, 1, or 2 defectives. Okay, so at least 2 means you could get 2. Oh, wait a minute. Oh, wait. No. No, this isn't right. It's close, though. You could get 0, but how many are you picking? How many are you picking here? 6. So I'm going to do all the way to 6. I'm not going to write them all out. They all add up. Because I'm picking 6 of them. There aren't only 2. Every one of them could be defective. Okay, so write all those out. You're picking 6, so we could have 6 defectives, 5 all the way to 0. Now, at least 2, circle or highlight what at least 2 means. And this is the part that's helpful. Are we including 2? Yep, and it's all of those. Now, do you want to add up 2, 3, 4, 5, 6? I don't. But what I would do is I would say, if this is what I want, probability of 1, probability of 2. Wait, why did I put the 1 in there? What's wrong? Get it out of there. Probability of 2, probability of 3, all the way to probability of 6. This is going to be the same as what? 1 minus probability of 0 minus the probability of 1. Now, which would you rather do? Add up 5 or add up 2? 2, yeah. So here we go. 1 minus the probability of 0 minus the probability of 1 is going to be equal to the probability x is greater than or equal to 2. So it's going to be 1 minus 6 choose 0, 0.3 to the 0, 0.7 to the 6th, minus 6 choose 1, 0.3 to the 1 times 0.7 to the 5th. Well, this one I know is just going to be what? Whatever 0.7 to the 6th is. It's 1 minus 1 times 1 times 0.7 to the 6th. And this is going to be 6 times 0.3 times 0.7 to the 5th. And that's going to be what anybody get that? 0.580. Okay, good. Now I'm going to take out my calculator and check you and see if you're correct. Oh, we're getting there. We're getting there. Oh, we're getting there. So, with this one, come on there, calculator. Coming up. All right, so everybody get your calculators out, and we're going to do this. Do you want to do this the easy way or the hard way? Hard way. Put each of these in 620.3 to the 0. Do each of those. That's the hard way. Really not smart. But let's do this kind of the smart way. I'm going to do this a couple ways. First thing I'm going to do is tell you where distributions are. It's second vars. It's above the vars there. And the distributions, we're going to use these a lot. You're going to go to binomial PDF first. Hang in there with the CDF. We'll get there. But PDF. And when I hit enter, it's going to tell me trials, P. It might not. If it doesn't, you've got an older calculator, hang in there, we'll be fine. I'm going to do 6, choose 0. Probability is 0.3, and the x value is 0 for this one. Now, when I hit paste, this is what you who don't have this feature, this is what you put in. Binomial PDF, 6, 0.3, 0. 6 is the trials, 0.3 is the probability, and 0 is the x. Now, when I hit that enter, I get 0.11764. 9. We're going to keep going. We're going to do the same thing, except we're going to do a 1 this time. So change that to a 1, and let's see what that one is. That is going to be 0.302. Now, if I took my calculator, 1 minus 0.1176, we're going to go 4 decimals, minus 0.3025, do you get 0.580? Yay! But there's more. There's more. You want to do it an even easier way? We'll look at it. We'll look at it. Okay, for PDF, it is the single value. But CDF is the accumulation from 0 to where you stop. Okay? So everybody listen very carefully. When I did this fun little thing here, when I wanted to do at least 2, did I stop at 1 or 2? Did I stop at 1 or 2? 1. When I start from 0, CDF, we're going to stop at 1 because I want 2 to 6. 1 minus P0, P1 will give me 2 to 6. So just go like this. 0, 1, 2, 3, 4, 5, 6. If I am stuck in my calculator with the number I put in is the last one I reduce, I want to reduce by these two, 1 minus this to get these. Is that all right? Some people have trouble with that. Some people don't. So then all you have to do is 1 minus distribution, go up to binomial CDF. It'll accumulate 0 to whatever I leave off on. I'm going to leave off on 1 this time because I want to subtract 0 and 1. A little confusing, but we're subtracting 0 and 1, so we want that to be the last. So if I did this right, it should be 0.58, and it is. Do you like that? Yeah. Takes a little time to go through, but I think it'll sink in. Let's do 2 other quick things. One is, love these problems that deal with shortcuts. The expected value, if you flip a coin 10 times, what's the probability of or let's see, flip it 10 coins, how many heads would you expect? 5, because what's 10 times a half? 5. So if you have a situation where the probability is 1/4 and you do something 40 times, how many times would you expect that to happen? 10, right? So n times p is my expected value. The one you wouldn't expect is the variance is npq. Would you circle those, box those two? These are going to save your life someday in mathematical journeys. An urn contains 7 marbles, of which 2 are blue. A marble is selected, its color noted, and replaced each time. So it doesn't change, it's independent. This is done 50 times. Find the mean. Okay? So the mean is going to be expected value, n times p. Well, we have n equal to 50 times. What's the probability of selecting a blue? 2 out of 7. So if I want to know the expected value, how many, if it's 2 out of 7 and I do it 50 times, can you see that it's 100 over 7? What you might not see, though, is the variance. The variance is going to be NPQ, which is going to be 50 times 2/7. By the way, what's Q? Yeah, if P is 2/7, fail is 5/7, or non-blue. And when you multiply these together, you're going to get 500 over 49. And if you want the standard deviation, you take the square root of that. The standard deviation, the square root of NPQ, or the square root of 500 over 49. I think that's 10 square root of 5 over 7.